Welcome back, and now we want to look at dynamical systems and see how dynamical systems behave when they have complex eigenvalues and eigenvectors. Okay, so here's a system, okay, and again we're in like Coyote and Roadrunner context, right? Like that's just the notation we're using. But anyway, we have a matrix A, right? So this is this 0, 4, 1, 0, that's going to be our matrix A. Okay. So we want to find xn and then look at the long-term behavior of x of t as we iterate through. So first thing, if you remember when we were first learning about dynamical systems, we eventually found things that we came to call eigenvalues and eigenvectors. So let's just go ahead and do that. Well, this happens to be the same matrix as in our previous video. So we saw that lambda was equal to 2i, and then the other value was negative 2i. Okay, and we found one eigenvector corresponding to 2i to be 2i and negative 1. And if we take the complex conjugate of that for the other one, it would be minus 2i minus 1. Okay, that's fine. Now, what did we do when we found the eigenvalues and eigenvectors? Well, then we wanted to find x0, right? We wanted to take x0, our initial state vector, and try and write it as a combination of the eigenvectors and eigenvalues. So, I mean, right, we can do that, but here's the thing. When we look at powers, so like nth powers of complex numbers, right, they make me sad because they're not that fun to compute. I mean, we can use de Moivre's theorem, we can use Euler's theorem to help out, but we're not going to. And then the other question I have is, if we want to look at long-term behavior, right, what's the limit of a complex function? Right, how do we do that? Okay, so that one's a bit of a mystery. We haven't discussed that yet. Okay, so here's another idea. Let's look at rotation scaling form. Okay, so if we look at lambda is equal to 2i, right? And then we said that that corresponded to the eigenvector minus 2i, or sorry, positive 2i rather, and then minus 1. Oops. So then that means that S is 2, 0, 0 minus 1. Yep. Wait, hold on. I have this backwards. And actually, I'm just kidding, because that's correct. That's what I wrote down. 2i minus 1, 2i minus 1, and then imaginary and real. Yep, okay, we're good. Okay, so then that means that when I look at S inverse AS, this is going to be 0, 2, the real and the imaginary part of the eigenvalue, and then 2, negative 2, 0. Okay, so that's nice. And previously we already said that this is the same as 2, 0, 1, minus 1, 0. Okay, that's fine. And if we wanted to continue to press on, right, I could apply S. I could, move the S matrices to the other side. So this could be represented as S and then times 2, 0, 1, minus 1, 0, times S inverse, right? And then if I wanted to represent that as a rotation matrix, this is really S times 2 times, and then we saw this in the previous video as well, cosine pi over 2, positive sign of pi over 2, and then minus sign pi over 2, and cosine of pi over 2, and then times S inverse. Okay, and so now this form makes it a little bit easier because when I look at xn of t, so I have matrix A, and now I just need to do matrix A n times the initial state vector? Well, this is going to be, and I'm going to abbreviate here, S times 2, and then C sine, or cosine sine minus sine cosine pi over 2. I don't want to write it out. Times S inverse, right? All to the n, and then times x0. Okay. And so then you can do this. Okay, I can write this out n times. Okay, this is going to be a little annoying. Bear with me. Okay, so this is going to be S times 2 times matrix times S inverse, right? And then another one, S times 2 times matrix times S inverse. I'm doing this to prove a point. S times 2 times dot 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 dot, right? And I do this, n times. But what is going to happen each time? Well, the S and the S inverse are going to cancel out, and the 2's can commute. Okay, and so then all I'm going to be left with is the final S inverse. So I'm going to be left with, rather, S times 2 to the n, because those can commute, cosine sine minus sine cosine of pi over 2 times S inverse, and then I forgot about x0 at the very end here, times x0. Okay, and so now remember those theorems that I forgot there's going to be n matrices as well. Okay, those theorems that we began with at the beginning, right? Anything to the nth power when we're dealing with sine and cosine, we can use de Moivre's, and that is going to allow us to say that this is going to be 2 to the n, and then it'll be cosine of n pi over 2 times sine, and then sine of n pi over 2 minus sine n pi over 2 cosine of n pi over 2, and then times S inverse times x0. Okay, so now this is the form that we really want to pay attention to. Okay, now the second part was, okay, we really want to know what happens as n goes off to infinity, right? And so that's where we can do a little bit of thinking, and you might use your imagination, like, okay, we have a scaling by a 2 each time, and then we're rotating by pi over 2 each time, so great, we're just going to rotate a quarter of a circle each time, and then keep scaling out, so it's going to blow up. Not a good thing, but anyway, that result is captured in this theorem. Okay, so if we have a dynamical system, right, we have x of t, blah, blah, blah. To get the next iteration, we have to take a matrix times the current iteration, and we have complex eigenvalues with associated eigenvectors, right? Then we can write x of t as r of t, I'll explain what r of t is in a moment here, times s, and then this is times that, so r of t and this matrix form that rotation scaling matrix. S and S inverse we've already discussed, so that notation we already know. R, okay, where we get r, it's the square root of p squared plus q squared square root, and those, if you can remember, those are the real and imaginary parts of your complex eigenvalue. Why they change from A and B? Probably because we have a matrix A and they didn't want to confuse you. Okay, so that's a summary of this, and now in the next video we're going to look at the long-term behavior of this. This is just kind of a summary of what we captured through this example up here. Okay, but keep this form in mind. We will be using it frequently in class, in group work, and then also in your homework.